Hello and welcome back to another video. This will be wrapping up decision trees, sort of a follow-up along to the first video introducing them. This one talks about the complexity of decision trees, some things to consider at an introductory level, just some things to be mindful of, and more reasons why decision trees are pretty cool. So first up is that overfitting is a real possibility with these. The decision tree algorithm is kind of different from the like a clustering algorithm, for example, and overfitting becomes a much greater possibility. And so in the last video, I made a small diagram that looked something like this, with a bunch of classes on one end and a bunch of other classes on the other end. Right, let's put some green ones over here. And so when you draw a decision boundary, it might look something little, let's say, like this. Right, where most of the greens are on one side and most of the oranges are on one side. Right, but you can see there's a couple data points that are classified inaccurately. Right, so your training accuracy isn't quite going to be 100%. It's going to be less than 100%. But if you're not careful and you just let the algorithm run wild, then your decision boundary might just keep looking for ways to classify more data points such that it'll look something like this. Right. And this will perfectly capture everything, but you can see how many zigzags and turns and curls that these decision boundaries have. Right? And while this might look good for perfectly classifying your training set, the moment that you get a new data point, something that's very similar to something that you've already seen, you can see that that accuracy falls apart fairly quickly. So be mindful of that. A deeper decision tree doesn't necessarily mean a better decision tree. All right, so we have a technique, we call it pruning. Pruning is a technique where we can trim out parts of a tree that may cause us to overfit. Right? Pre-pruning is by making the decisions for how deep you want your tree to be prior to actually learning it. But post-pruning is that you can make the full tree and have as many layers and levels as you want, but you just pick and choose the ones that you ultimately keep. The easiest way to understand this is if we then draw out our tree again. One more level down low. So we have a binary tree here where at each level there's only 2 decisions we can go in. In some cases you may have 3 or more, but just for simplicity's sake, we're just looking at 2 here. Right? We could say that we have a tree this big that will, let's say, divide the levels up here just so you can see a little clearer. Let's say this tree right here actually gave us these decision boundaries, right? But we don't want something to overfit like this. It's a little too tight. We want to loosen the restrictions a little bit. So we might study the tree and find that, well, this feature doesn't actually tell us too much about our data points, right? Or we could say that information is already captured in another part of the tree. So we might just get rid of it altogether, right? Which would then merge these 2 boxes. So once you go along this point here, you're actually at the point where you have to make this decision at this level down here, right? And let's say you get rid of that tree, right, which causes this boundary to disappear, and then, well, you have a smaller tree and you have a little bit worse training accuracy, but let's say you then had a data point to come in over here, then you'd still classify correctly as an orange data point. Right? And these green data points would be treated as just outliers that are unlikely to happen again. Right? Which then could then boost your algorithm's ability to generalize to new data points, which is what we want at the end. Okay? Deeper trees can be more complex and overwhelming, but again, if you're working with decision trees and programming frameworks, scikit-learn, for example, that's a popular one that people use when doing their or creating their algorithms via code. There are ways to produce visualizations that look just like this one here, and also ones to produce visualizations like you see here. So I don't have any examples for this video, but it'll look just like I've drawn here. And so if you do experiment with these in the future, I just recommend that you be mindful of them and be aware that they exist if you want to take a little bit of step further just to get a better understanding of how your model looks and how it performs. Okay. Now that's for visualizations. There's also analysis tools that exist. And probably the most important one is this thing called feature importance. I mentioned in the first video that our classes are these leaf nodes right here, whereas our features are where we are making these decisions. And like I mentioned with the box that used to be here, turns out that feature wasn't very important. So we actually just scrapped it and got rid of it altogether. Right? And feature importance will give you a rating between 0, it's not a pencil, between 0 and 1, depending on how well it actually predicts the target data. Right? So the remaining features that we have here are ones that give really good insights into what class our data point might belong to. Just expand upon that a little bit. Just because a feature receives a low score doesn't necessarily mean it's a useless point. Right? It could be the case, like I mentioned earlier, that a data point, rather a feature that we encoded into this decision block is actually already captured in a different decision block. Right? So for example, the number of beavers in a forest is likely to correlate to the number of trees in a forest, because beavers like to, chew up trees and make their logs and build their dams on rivers and whatnot. So the more trees there are, the more beavers are likely to be in a particular area. So if we look at the feature that says, look at the feature that says this is the number of beavers, it's greater than 100 or less than 100. But this says, is there greater than 1,000 trees or less than 1,000 trees? That information is likely to correlate, and so we can remove the need for a feature like this, just so our tree can be less cluttered and give us a better decision boundary once it's fully trained up. Also note that feature importances are not to be seen as law, and you could take the same data sets and run your decision tree learning algorithm on it several times and get completely different outputs, right? Because the algorithm learns things that aren't quite as obvious to the human mind, and so whatever our algorithm produces can be different from time to time. And so just because in one iteration of the algorithm says that the number of beavers isn't important, the next time you run that algorithm on the same data, it might actually say that number of beavers is really important. Right, so just be mindful of that. You may want to train your data a couple more times. There's this neat technique called ensemble learning that I'll talk about in a later video that'll show you how to take advantage of the results from multiple decision trees and aggregate them together into a potentially better model. So, in summary, decision trees, model complexity is controlled by the pruning and the test selection. Right? This contrasts with the model complexity for regression and clustering, or clustering, k-means algorithms. It's different in this case because pruning doesn't exist in the algorithms we talked about prior. Neither does test selection per se, except if you're making a decision boundary off of regression, whether you're above or below the line. And another important note is that you can actually use these for regressions as well as classifications. So in the example I drew up here and in the previous video, we're classifying, are you a member of the green class or are you a member of this orange class? But you can also probably won't go into a full-fledged example here because it's less likely that you'll use these. Actually, that might even be bad. Let's come back down here. We'll go in this small corner down here. So again, we have our graph, and we have our data points that follow somewhat of a trend. All right, and let's say our regression line, if it fits the data, it looks something just like this, right? But we could use our decision boundaries and may look something like this. All right, much more jagged line, but this is a means of figuring out the regression of the data points using a decision tree, right? But the note I have here is that unlike your linear regressions, if you're using decision trees for regression problems, you cannot train based off of information that is outside the feature space. And so let's go back a little bit, get rid of these lines here. All right. If I were to use this training set right here with these white data points, I can only learn based off of information that is within the domain of the training information. That means this point up here, I can only learn based off of everything that is below and behind, right? So the moment I get a new data point, let's say it's somewhere over here, this algorithm will not be able to classify that. It won't know anything going on outside the feature space. As a matter of fact, if I were to tell it to make a prediction beyond this point here, it's probably just going to be the exact same point. If anything, it might just make a straight line going out. But any data points outside the feature space will not make any sense to the algorithm. So that's a crucial thing to keep in mind should you decide to work with this for regression purposes. Okay. And lastly, decision trees have two major advantages over the algorithms we discussed previously. That's linear regressions as well as k-means, or k-nearest neighbors, I should say. K-needs and k-nearest neighbors are very similar, but decision trees have two major advantages over them. One is that they can be visualized very easily. And the number of examples I've given in the past couple of videos, these are great visualizations for understanding how is your information being learned on and how is it classifying differently. And they're built-in tools to the existing frameworks that help you do that. And the second example is that they are insensitive to scaling and representation of the data. So usually, if you're working with different regression problems, let's say you have a lot of features and those features are represented with continuous numbers. You may have one feature, like the population of a city, that can be up in the millions of people. 1 million, 4 million, 10 million, 13 million people, right? But then you might have another feature, something like the average number of cars owned by a family, which is probably 1 or 2, maybe even 3, right? And when you have these numbers, usually in machine learning, bigger numbers are going to be treated with more importance. And so you could come up with a different problem that pertains to city population, average number of car zones, for example, the CO2 emissions, the carbon dioxide emissions that a city has, right? It's going to treat that city population much more significantly than it would the number of cars, just because it's a bigger number. But we know in reality that doesn't always guide us to the right solutions to our problem. Right? But for decision trees, it doesn't necessarily matter. We can say, does this city have a population above 1 million or below 1 million? Yes or no. Is the average number of cars owned by a family above 2 or less than 2? Right? Yes or no. Right? you're basically making a yes or no decision based off of that. So however outrageous the numbers could be, however big or small, these decision trees don't really keep that, or they don't factor that into the tests that are learned in the algorithm. So that's one really good thing, because the less that we have to manipulate the data, the more raw data we can use, typically the better our learning algorithm will work. So that will cover the complexities of decision trees. And in future videos, we'll talk more about combining different trees together in ensemble practices to get better decision trees for different machine learning problems. So thank you for watching.